claim, we're asked to show that the limit works nicely with subtraction, essentially. So we are allowed to assume that Sn already converges and goes towards S, and that Tn converges and that it goes towards T. We do have to prove a limit here, so I'm going to start off with the classic let epsilon greater than 0 be given. So I know epsilon is given. Now, since Sn converges towards S, we know there is a capital N1 such that when n is larger than n1, we have that Sn minus S can be made less than any positive number. So I'm going to make it be less than epsilon over 2. Similarly, we know the same thing for T. So similarly, since Tn converges towards T, we know there is an N2 this time, such that when n is larger than n2, we have that Tn minus T can be made less than epsilon over 2. So we have an N1 and an N2 that make Tn get close to T and Sn get close to S. How close? Half an epsilon away is how close. So we will now choose our capital N. We will choose n to be equal to the maximum of these two guys, N1 and N2. So that way we're making sure that the Sn's getting very, very close to S and that the Tn's are getting very, very close to T. So if n happens to be bigger than our capital N, which is larger than N1 and N2, or bigger than or equal to N1 and N2, we have, let's go through it now, last part, Sn minus Tn minus S minus T would be exactly equal to, with some reordering, Sn minus S and then a negative plus a negative of a Tn minus a T. Okay. So by the triangle inequality, we can now say that this is less than Sn minus S plus absolute value of the opposite of Tn minus T, but that's just the same as Tn minus T. And because we chose our n appropriately, we know that this is less than half of an epsilon plus a half of an epsilon, and that's literally just epsilon. So that completes our proof of the limit distributing or working nicely with subtraction.